I'm privileged to present my work previously in front of you, and very much honored to be part of this group. We just had a very heavy lunch, so please excuse me if I'm over the time slightly, but I'll try to cover it within the allotted time. So do not really go by the title too much, because it's kind of a conjunction of two different spectrum of research, one on globular protein, one on disorder protein, and this actually is an area where I want to go in the future more. So I haven't really done too much of stuff on this. So addressing the globular disorder interface in proteins from a protein design perspective. I'm not really describing from where I did my previous postdocs, etc. Just let me tell you that I'm basically a structural bioinformatician, or have also done some computational biophysics. So first I'll try to describe these two functions. They are the very fundamental rule of thumb functions for structural bioinformatics. This was developed, virtually developed by the same group, one in 1993, the other one in 1997, for protein-protein interactions. So this is called shape complementarity, this is called electrostatic complementarity. They are the most two fundamental attributes protein-protein interface of any kind of molecular interface can have, and they are very much necessary and sufficient conditions for large molecular surfaces to associate specifically. So in order to compute this, you have to generate the Connolly or the molecular surface of the two interacting partners, and these are essentially dot surface points. So they are area elements, and so they have a direction, they are unit normal vectors. So you have to take, first you have to figure out the nearest neighboring dot surface points, so they become two troughs of ordered pair values, and then you have to take the dot product of these two unit normal vectors, one taken outwardly, one taken inwardly, to render a positive value for perfect correlation, and then you multiply this with an exponential term of the distance square, where d is the distance, w is a scaling constant. So essentially this takes care of the fit, the geometric alignment, as well as the distance between the nearest neighboring dot surface point. So for example, if you have very good shape correlation at a very close proximity, and if you increase the distance, that eventually spoils the correlation as well. So both this proximity and the alignment is important. And once you have, let's say, 1000 dot surface points, you come up with 1000 pair of nearest neighbors. You compute this value for all these 1000 pairs and get the median of this distribution. That is essentially your shape correlation of these two interacting surfaces. And median is a better measure of central tendency for this kind of distributions, because they are negatively skewed. But essentially they are non-reciprocative. So that means if you have let's say a value of x for this dot surface point taken as the target and this as the neighbor, it doesn't essentially mean that when B is taken as a target and A is taken as a neighbor, it will have the same identical value of shape correlation, because simply because of the fact that this is basically a reductionist approach. This is not the entire picture. This surface point may find this as its nearest neighbor, but that will not guarantee that this will also find this as its nearest neighbor. It will find some surface points nearer to it than this one. So it's basically packing between nearest neighboring dot surface points. So this function, when they computed for all protein-protein complexes at the protein data bank at the time of 1993, irrespective of the biological origin, whether they are protein inhibitor complexes or antigen antibody complexes, they raised a certain range of values which fall in the bin of 0.6 to 0.7. So this is essentially a correlation function, varies from -1 to +1. More you approach +1, better is your shape correlation. So the origin of the interaction was irrelevant. So once it exceeds a certain area cutoff barred upon complexation, it has to satisfy very strong stringent constraints on shape correlation. 4 years later, the same group came up with this measure of electrostatic complementarity. It's simpler actually. So you have to sample all the dot surface points just like this one, and then you have to compute the electrostatic potential by iteratively solving the Poisson-Boltzmann equation. And you have to compute this twice for each dot surface point. Once due to the source atoms of the charged atoms of the source molecule, and once due to the charged atom of the partner molecule. So each time the atoms that are not contributing to the electrostatic potential, they are treated as dummy atoms. That means they are only assigned the van der Waals radii, no partial charges are assigned to them. So anti-correlation, a high anti-correlation will actually mean complementarity in terms of electrostatic potential. So surface electrostatic potentials are anti-correlated. So that you can see whenever you find a very high negative, which means positive, blue, which means positive potential here, you get negative potentials for the complementary or interacting surface. So you have to then take you end up getting two troughs of electrostatic potential values, and the negative of the Pearson's correlation gives you the electrostatic complementarity. So similarly to that of shape complementarity, when they found out, when they computed this value for all protein-protein complexes that time in the protein data bank, they found out that they also range to a very similar mean of values, let's say 0.5 to 0.6, irrespective of their biological origin. So combining these two, what we did, we probed the protein interior of all globular proteins. So what we did essentially, we computed the same thing within the protein interior. The idea was whether, based on the concept of complementarity, we can bridge the gap between binding and folding. So in a sense, binding could be envisaged as the docking of the interior components upon the folding of the polypeptide chain on itself. So what we found out is very similar to their results, that irrespective of the chemical identity of the actual amino acid residue, all amino acids have to satisfy very stringent thresholds in terms of both shape and electrostatic complementarity. Obviously, the error bars are larger for these gray bars, which are the electrostatic complementarity value, with respect to the black bars, which are the shape complementarity value, because of the sources of the force, the van der Waals and the electrostatic interactions, they comes from a long range and short range nature of forces. So this is very consistent. So utilizing this information, we then formulated scoring functions like these ones, where we ask the question that what is the range of shape complementarity and electrostatic complementarity given a particular amino acid type, let's say valine, and a particular burial, let's say it is completely buried within the protein interior. So essentially then this is a conditional probability, and then we could multiply them to find the joint probability of their co-occurrence, and then average it over all buried or partially buried residues within the polypeptide chain. So we use this successfully to identify the native fold amide set of decoys. I was going through the literature from this laboratory, and I found out very similar approaches, not computationally or from the perspective of designing a scoring function, but here also we have tried to address the fold recognition problem. So this is one of the attributes of the fold recognition problem. The other one is obviously cross-threading. When you have a very low sequence identity pair of proteins, whether they give rise to the same fold, that is another level of complexity, and we could also successfully address the cross-threading problem as well. Now, using shape and electrostatic complementarity, we designed this structure validation tool called the complementarity plot, which is in design very similar to the Ramachandran plot. You have phi and psi in the Ramachandran plot in x and y axis, both varying from -180 to +180. Here we have shape and electrostatic complementarity, both varies from -1 to +1 in x and y axis. Analogous to allowed, partially allowed and disallowed regions of the plot, we have probable, less probable and improbable regions, but this is deterministic in nature, this is probabilistic in nature. So this is knowledge based, so you have to rely on high resolution protein crystal structures to enumerate these contours. Whereas in Ramachandran plot, Ramachandran did not have the privilege of having all those crystal structures at his time. He only had a few peptide structures, and this was actually drawn from first principle of steady clash. So here, once you have these contours, I can give you an atomic model, whether it's a modeled one or a crystal structure, anything, and you can simply compute the shape and electrostatic complementarity of side chains and you can put it in the plot and see how much they are scattered and or vice versa. I mean how much they are constrained within the regions. So and then if you really find a distorted distribution like this one, you can go back to the electron density map and see whether there is a fundamental error in threading the main chain or things like that. So this was also one very crucial point I want to mention, that in case of a sidechain prediction problem, or where you can generate decoys by randomly threading the side chains, the same identical side chains on a native polypeptide chain, you should have identical distributions of a native and a decoy in the Ramachandran plot, because virtually they have this identical backbone, but you will obviously have drastically different distributions in the complementary plot, because they are side chain functions, whether a side chain is harmoniously placed with respect to its local and non-local neighborhood. It has many applications. I'll just focus on one application which was very interesting. So we picked up a series of protein crystal structures, and then we performed in silico mutations on all 4 residues. So replacing residues with alternative hydrophobic character, but trying to maintain the shape and size as much as possible. For example, alanine going to serine, threonine going to valine, phenylalanine going to tyrosine, and like that. So effectively we spoiled the interior or the core of the protein by forcefully placing a lot of partial charges. So in principle they will never fold like if you have these kind of sequences, but this was like a test for false positive, whether the method can detect those false positives. So what we found, false negative, I'm sorry for that. So what we found was very interesting, that when we did energy minimization with a flexible backbone to remove all the steady clash, even functions like mol probity softwares which are kind of recommended by the protein data bank, they are unable to detect such errors, simply because they don't have any electrostatic splitting component. So when we put these in the complementary plot, obviously we found that all these erroneous residues are quite well detected on the negative quadrant of the EM axis. Obviously they don't have any problems with shape complementarity, and which reflects in this very high negative score of the Loward score as well. Now I'll try to go into packing in a little more detail. For that we wanted to find out that whether the three-dimensional jigsaw puzzle model was actually applicable in context of globular protein interior. So that means whether a specific geometry has a constraint on a certain type of repetitive patterns in packing topologies within protein. So for that we first did put constraints on shape complementarity and overlap to pick up the geometrically specific interactions, and within that domain we tried to identify each and all networks, all small graphs, and using this numeric scheme. So for that you have to compute the degrees of each and every node, and then you have to figure out what are their nearest neighboring nodes, compute their degrees, concatenate with the degree of the source node, and then have these number strings, sort it in descending order and join them by a delimiter. So by this kind of a numeric formalism, you end up representing this graph into a single numeric value which describes it in a non-redundant manner. So it's a topological identity of the same graph. So using this numeric scheme, what we found out that there were 2 essential large families of motifs. One were termed, one is an open linear chain, or in graph theory terminology we call them tree, and the other one is the family of triplet cliques, where there are close association of 3 hydrophobic residues at the core interacting in a geometrically specific manner. There were 13 families in all, but the other families were found in absymally low frequencies. So when the larger networks were focused, we found out that we could actually implement a nucleation condensation model of protein packing. That means using this as a non-rigid basis set of motifs, we could actually have a linear combination of for the larger networks using like a linear algebra problem. So effectively using these as the basis set. So one of my future aims would be to try to implement, try to incorporate a triplet click within an existing protein with low or lower thermal stability, and see whether that actually helps in increasing the thermal stability of the protein, because these clicks have been found ubiquitously regardless of the actual three-dimensional fold of the protein in each and every fold. So and for example, if you have this kind of an open linear chain like an angle which is not closed, you can simply make one particular mutation to make this form a triplet click. So it's very simple to use, it's non-covalent, that is another very interesting aspect of it, unlike the designing disulfide bridges which are kind of irreversible because of having the covalent nature. So this is something I want to explore in the future. So now I'm going into the other attribute, like for disordered proteins. So for that we first try to use the same numeric formalism to identify all the salt bridges within the context of globular, disordered and protein-protein complexes. So as we can expect, the isolated salt bridges were the maximal, they came at a maximal frequency followed by a bifurcated salt bridge. So here we can have arginine at the center and you can have glutamate or aspartate and vice versa, obviously, because remember, other than lysine, all the other charged residues including histidine, they have two degenerate polar groups. So when we looked in more detail for the bifurcated salt bridges, we found that they could be used as clipping protein-protein interfaces or stitching the protein-protein interface because they have three like this fork-like structure, and these salt bridges could be proximal with respect to one another, and they could be sparsed around the whole interface as well. This is one of the functional attribute of bifurcated salt bridges. We also found that there was complex and composite salt bridge motifs, like we call this one a 4-star in graph theory terminology. We call this a quadrangle. So this I should actually emphasize a little bit, that people have never found a successful end result of a salt bridge design. There is no such stories in the literature as yet. And why is that? Because one has to deal with enormous amount of computational complexity with regard to the side chain rotameric space. As you can see, arginine has 64, lysine has 57, glutamate has 36 rotamers already tabulated in the Dunbar's library. So if you are trying to design a single salt bridge, you are basically selecting one order pair combination out of a combinatorial space of, let's say, 64 into 36 if you are trying to design a arginine glutamate isolated salt bridge. So it's very difficult. So one of the possibilities is that, this is again something one has to explore, that if we can try to design a composite salt bridge motif rather than trying to design collection of isolated salt bridges. So we may not end up getting exactly the desired salt bridge motif, but in a sense we are increasing the local charge density at a certain region. So that will probably increase the possibility or the plausibility of having it, the rescue of the design salt bridge. And this is very similar to designing alternative packing states in hydrophobic core of protein. So people have found that a particular hydrophobic core may not be resultant out of a certain topology. A combination of topologies can give rise to the same fold, as long as certain global constraints are matched. So then we went to the domain of intrinsically disordered proteins. We picked up 4 of them, 2 completely disordered and 2 partially disordered, and performed molecular dynamic simulations on them, 100 nanosecond trajectory. Even there we found these complex motifs, and they were kind of persistent at least through 1/4 of the MD simulation trajectory. Our essential question was that intrinsically disordered proteins are known to accommodate an abundance of oppositely charged residues. So how does it affect the flexibility, the very well characterized high degree of plasticity of the disordered proteins? Because if you are trying to, if you are accommodating an abundance of oppositely charged residues, it will invariably trigger the formation of salt bridges, which will be paradoxical in the context of retaining the desired flexibility. So how come these two seemingly opposite phenomena can coexist simultaneously? So that was our question. So what we found out that when we did a calculation of persistence of all the salt bridges, we found out it had an exponentially long tail, and if we just highlight this particular portion giving a certain cutoff, so persistence means how many times in the trajectory the salt bridge appears, as simple as that. So when we magnify this particular region, we find that there are very stable salt bridges, like very highly persistent salt bridges, there are moderately persistent, briefly persistent, and we may call these as fleeting or ephemeral or short-lived or transient salt bridges. So an inherent tendency of this kind of research is to throw away this tail, assuming they as the artifact. But actual mystery lies in this particular region, what we found out later on and what I will show you in the next slide. So this is very interesting that these fleeting salt bridges, they actually continuously change their binding partner. So for example, this particular lysine, I have just, for pictorial clarity, I have just picked up 4 conformations here. So this lysine is actually making salt bridges with 4 different negatively charged amino acids at different time points of the trajectory, of the simulation trajectory. So in a sense, it is bringing close together different regions of the polypeptide chain, and that's one of the reasons why. And imagine this is happening throughout the chain with all the salt bridges doing this simultaneously, all these splitting salt bridges. So what will happen? Different conformations will be supported at different points of the empty simulation trajectory. So that is the inherent mechanism by which probably a transient nature of salt bridge dynamics can retain the conformational flexibility or the high degree of plasticity so characteristic to intrinsically disordered proteins. Now the reviewer asked a very interesting question. Now obviously we did not have the privilege of having any experimental data. So his question was to whether can we justify that this is something functionally optimized. What is the implication? Okay, we understand that there is this kind of mechanism probably coming out of your analysis, but are they functionally optimized? So to address this question, we did a number of mutational studies also, which I am not showing here. I am just showing a docking study which we performed on the empty simulation trajectory itself. So this is alpha-synuclein, which is the candidate protein for Parkinson's disease, and this has 3 domains. One is the N-terminal, C-terminal, and there is a middle purple domain, and this purple domain is devoid of any charged residues. And a very well-known binding partner is tubulin, which is a globular protein, all helix. No, not all helix, alpha plus beta protein. And as you can see, so people have identified which region. They have kind of identified the whole binding phenomenon other than structural perspective. So they know that which region the tubulin binds by immunoprecipitation assays and all. So we use those informations and we docked on the simulation templates this tubulin, and what we found out was very interesting that initially this is an open conformation, and then it kind of wraps around the tubulin molecule where these salt bridges are getting disrupted and forming salt bridges with the tubulin molecule. So that means there is a conversion of intra-chain salt bridges going into inter-chain salt bridges. And now when we looked at individually that which salt bridges are actually going through this transition, we found out that it is the fleeting salt bridges. It is not those which are the persistent ones. So if you look at this distribution, there are these salt bridges which are kind of persistent, which stays there for long, and these are, let me tell you, they are generally formed with very short sequence separation. So that means we don't have to bring together 2 distant parts and keep them close all the time. So they are short range contacts. and then there are these fleeting solvages which are forming and collapsing all the time. So one of the very logical explanation to this problem is that well, the salt bridges are there, they are of fleeting character, they are forming and collapsing, and this actually makes them amenable to interactions when it is required. So they are actually the ones which are forming these interchain salt bridges. I'm not going to detail of this slide, only to say that this is a graph theoretical problem, classical graph theory problem called the chromatic number or the graph coloring problem, which I did something on with one of my mathematical friend. The problem is that given a graph, you have to label each and every individual node of the graph in such a manner that no two adjacent nodes share the same color. So this is a non-deterministic in polynomial time domain. We call it NP-hard problem. So we used a heuristic to solve this. It's currently under review. But the important thing is that this can be used as a bottleneck filter in protein design pipelines. So what we found out that there already are literature on the interface between globular and disordered proteins. People have worked on them, not exhaustively of course, but there are some evidences, and where there are crystal structures of design proteins as well. So we took these crystal structures of the design proteins, whatever was available in the protein data bank, and we found out that invariably, if you, irrespective of the actual topology of the contact networks, they were the chromatic number or the colorability of the graph, bent to a certain very small tiny range, which is like 2 or 3 colorable graphs. So this can actually be used in the context of protein design. So my basic idea is to, in the long run, whether we can come up with a scanning mutation library, for one particular globular protein and its evolutionarily ancestral disordered partner. So one can switch between these two, dialectically opposite domains of proteins. In the future, I would also like to address this question, which is very interesting, called fractal of disorder. Likewise, we found the transient salt bridge dynamics within in the context of salt bridges within intrinsically disordered proteins. There are brain disordered like epilepsy and other neurodegenerative disorders where there is a known term which is called, there are two parameters basically, burst size and burst durations, and both of them follow power law distributions, and by which they have termed these as, this is basically going between two unstable steady states. So there are transient dynamics in brain disorders as well. So basically there are multiple unsteady steady states, and the system can hop or swap between different unstable steady states, and there is a similarity, apparently there is a similarity with the transient dynamics of the salt bridges, which has been revealed in intrinsically disordered proteins. So if we can formulate measures, equivalent measures to that of burst size and burst durations in context of the salt bridge dynamics in intrinsically disordered proteins, and see whether they also follow similar power law distributions, so then there might be a bridge between disorders of different hierarchy, so which will reveal a similarity or a fractal nature of different dimensions of disorders. So that's all I wanted to share with you. I am grateful to my all these mentors that I have worked with, especially my PhD supervisor, Professor Rahul Banerjee, and thanks for your patience. I'll be happy to answer any questions. Was it too heavy in content with respect to time?
Yeah, I think you could have said a bit less, a bit slower. But
so you're talking about salt bridges which are transient, but are they more often transient than other types of interactions like H bonds, aromatic interactions, getting by? specifically looked at transients of salt bridges?
That's a good question. We didn't really look at hydrogen bondings or other interactions separately, but obviously in intrinsically disordered proteins, electrostatic interactions is key, is much more relevant than in a comparative sense than in globular proteins with respect to van der Waals and other kinds of interaction. So amongst electrostatic, within the domain of electrostatic interactions, you have dipole-dipole interaction and charged dipole interactions, hydrogen bondings. Salt bridges essentially is one of the key components. And our fundamental question was that how come the disordered proteins contain so much of oppositely charged residues and still can retain their desired flexibility. So from that perspective, we studied salt bridges, but obviously one can have a comparative analysis between other kind of interactions as well.
And did you see a difference between salt bridges that contain lysine or arginine? Did you look at that or not?
Not specifically, but I remember that beta amyloid, which is a 42 amino acid long protein, doesn't actually have an arginine.
Yeah.
But the only notable thing is lysine is the only amino acid, charged amino acid, which will never form a bifurcated salt bridge because it's just one polar group. The others, every other charged amino acids can form, in principle can form bifurcated salt bridge. But I don't think it will matter much because here we are not really looking at motifs, rather a collection of salt bridges, isolated salt bridges.
I have a question. I'm not sure I understood how this is related to molecular evolution, what you talked about. Maybe I missed something.
So the basic idea is that one can choose salt bridges to as a point of mutation,
Yeah.
to select for which residues one wants to mutate in order to form the scanning mutation library.
So as a selective advantage.
Yeah, I mean, what we did, I am not showing that data. We took beta amyloid, which is a 42 amino acid long residue. We separately did two in silico mutations, like two series of in silico mutations. In one case, we mutated all the high persistent salt bridge forming charged residues to alanine. In the other one, we mutated all the transient salt bridge forming residues to alanine. And we